Great. Hello, everybody. Welcome to this episode of the Biznerd podcast. Today, I have with me Nikhil R Gupta of Determinant Materials. Before I get started on his intro, I have to thank Amit Ajwani, a friend on Twitter, who actually did a tweet thread on Nikhil, which is how I found Nikhil. So thank you to Amit and go follow Amit Ajwani on Twitter. He's a great Substack about hard tech, so check that out. So Nikhil is actually the founder of Determinant Materials, and they're doing some really breakthrough work in terms of metal extraction from waste. Their core technology it's called the microrefinery technology, patent pending. Nikhil is actually has a background in process engineering and chemical engineering, and has worked in everything from an oil company to consulting, and he's jumped into entrepreneurship. So I think this should be a fun episode. So I'm gonna go ahead and welcome Nikhil. Nikhil, thank you so much for coming on today's episode. This is an absolute honor. Thank you for coming on board.
Yeah, and thank you for Pranesh for having me. And also Amit did a great job on that tweet thread.
Yeah, Amit is really great. He actually understands hard tech, which is a difficult thing to do. So I just wanted to start off by asking you, what sparked your interest in engineering?
Yeah, I think there are always long answers and short answers to these questions. I think maybe the long answer would be, as a kid, I was really interested in science and technology. I had this book, it was called Pocket Science, and it was all different segments on different topics of science, like mass, energy, specific aspects of chemistry, things like that. I just remember as a child getting really excited and interested in this sort of thing. And I remember the author, I looked on the back cover, it said the author was an engineer. Like at the age of 5, I had no idea what that was, but it was something interesting and it was in the back of my mind. You fast forward a couple of years, I'm sure my parents had some aspect of doing that, cultivating that interest that I had. But I remember in middle school at one point, I read every single, I believe I read every single science book in the middle school library at the time. So it was just something that kind of built over the years as a kid.
Yeah, and that went from a curiosity to a serious commitment when you enrolled in the Olin College of Engineering, and which is interesting because it's not. I went to Purdue, which
Yeah.
is essentially a factory for engineers.
Yeah.
It's a chicken factory for engineers. But you went to Olin, which was a sort of smaller, private liberal art college approach to engineering. And the only college like that I'm familiar with is actually Harvey Mudd,
Yeah.
which a high school classmate went to.
Oh, okay.
Talk to us a little bit about your experience going to Olin and how
Yeah.
that shaped you.
Yeah, sure. I think fast forward a couple of years, I grew up in Connecticut. My family's from New York City. I remember one summer I was staying with my grandparents in Staten Island. That's one of the outer boroughs of New York City. And I was interning at SUNY State University of New York Downstate Medical Center in Brooklyn. So I remember I was doing an internship there, and it was college application process. I assume I was probably a sophomore or a junior, and I remember talking about engineering schools because there were people who were biomedical engineers there. And then one guy who had gone to a really high-end school in New York City for high school, Stuyvesant, he had mentioned, hey, one of my classmates at Sty went to this new school called Olin. And I said, oh, Olin, what's that? As a kid, you expected, okay, what your top was like going for an Ivy League school or going for like an MIT or a Carnegie Mellon, that kind of thing. So that was a big research university, brand name kind of school was what I had aimed for initially. But I looked into this school and I heard about it and I went on the website and I just started reading about it. I was like, wow, this is really pretty amazing. I think what really got me about Olin, and the full name is the Franklin W. Olin College of Engineering. So we're all engineers there. It's purely engineering. The big thing is they talked a lot about, they had this Olin triangle: design, engineering, and entrepreneurship. So the idea was like, okay, you go out in the world, in society, and see what people want and what people need, and you design the sort of solution for them. Then you take that and you run with it and you engineer the solution. And then from there, you use business and entrepreneurship to actually get it out in the world at scale. So that's like idea of, hey, you define the problem for the world and you go through the full life cycle where you can actually bring it to the world, bring your idea to fruition. That was something that was really excited me. And also, as part of the college application process, I had figured out for myself that I really wanted to, yes, one, do engineering, but also be an entrepreneur, and specifically in the clean tech domain.
Yeah, and I think I mentioned that like my one of my classmates in high school was in he ended up going to Harvey Mudd. I think like it's interesting that you describe Poland in such a way because Harvey Mudd also had a similar thing, and I was like, you can get this out of an engineering university because my experience of engineering is you are expected to go through a bunch of prereqs, but like ultimately like it's your responsibility to make sure whatever experience you want is had by you. So that's kind of interesting. It's kind of like a Montessori approach to engineering. Is that Montessori school, right?
I've
Yeah,
heard of it.
it kind of feels like that.
Mm.
Yeah. And while you were in Olin, like you actually went and worked on this Ghanaian village, and you worked on this plant that did like cassava processing, which I found very interesting.
I was wondering if you could talk more about the lessons learned there in terms of engineering, entrepreneurship, and anything else you might have learned in that process.
There was a class called Affordable Design and Entrepreneurship, and it's centered around basically figuring out how do we design, again, scalable solutions in developing countries for things society needs. And again, the premise was like, look, we're not an NGO, it's not about charity, it needs to be scalable. So it needs to be something that basically in effect can make profits scale internally, right? So the idea was actually to go to these developing countries and help people set up businesses there that they could improve their livelihoods, right? If the audience has looked into things like microfinance and such like that, it's somewhat similar. Like, how do we set up these businesses? But it was heavily based like engineering and technology based. So a couple of different groups. The one I was in was based in the country of Ghana, right? We were in school in Massachusetts in the Boston area. And ultimately we were trying to build technology products and businesses to be used and operated in Ghana with certain end markets. Quick background a bit. There's a crop called cassava. It's like a root, a tuber. It's what tapioca is made of. So it was one of the kind of like staple starch food sources of people in Ghana, and I think probably heavily the villages. The idea was basically there were a certain subset of the village. Usually it was women that would produce the cassava and turn it into something like an actual food source, right? So if you can think of, okay, the farmer grows the grain, the mill is turning the wheat into the flour, something similar. So they would take the cassava and they would turn it into something called gari, which was one of their staple food sources there. That was a long preamble. But basically, in effect, we were trying to figure out how do we make the lives easier of them? How do we help them churn out more product, in effect? How do we churn out more of this cassava flour that they can feed their families with, but ultimately they can use in their business to sell to other people and grow the scale and scope of their business. And essentially what we came out with is mechanical devices that would help grate the cassava much easier. And you have to think about it, like, we weren't building this for the United States, right? We're building this for sort of the electrical infrastructure that was present there. This is years back, but I remember even 220 volts, I think, which is here, I think it's 110 or 120 usually in the United States. So it was different voltage. I remember installing the inverter. I remember shocking myself off the 220 volts a couple times. Different realities, or not the kind of same reliability that we would have in the United States. So really interesting challenges there. And basically you learn how do you build a business that is helping society with certain constraints and for a certain customer end group. So it's a lot of the kind of like customer discovery, understand what they want, understand their motives, understand, and then of course the technology. One of the aspects, the one I spearheaded, was actually cassava actually has cyanogenic compounds. That means inside the starches, there are cyanide groups, right? So cyanide is a poison. I mean, they literally use that to poison people. Over the years, over the millennia, humans have figured out with their processing methods how to detoxify, decyanify the cassava. So I was working on, hey, look, if we are like speeding up their production rate, we need to focus on this too. How do we make the detoxification a better, more efficient process?
And you then went on to graduate and then work at Shell, where you did a bunch of process engineering. And I feel like that's where you really got like your grounding as a chemical engineer.
That's correct. Yeah. If we backtrack a little bit, I mentioned briefly the college application process. One of the things that kind of shaped my sort of like my worldview and my kind of my mission in life is going through the college application process. You have to figure out, examine your life. What do you want to do with your life? So one of the things that that was basically a big impact for me. And again, it's similar veins here, right? So when I was 14, like right after freshman year of high school, I went to India. And I was born and raised in the United States, but the family's from India. And so I went to India by myself. I stayed with family there. And this is like in the mid 2000s. The country has definitely advanced a lot since then, but at the time, there was huge energy and resource insecurity and massive amounts of pollution. There still are in certain areas, but it was a big challenge back then. So I'd be sitting in my cousin's shop in the capital of India, Delhi, and it'd be like 120 degrees out during the summer, huge amounts of humidity. And all of a sudden the electricity goes out, right? So you lose the lights, you lose the fan, you lose the AC. So no energy resource security, but huge amounts of pollution. You can barely breathe the air. There's huge amounts of groundwater pollution. Combining that with the interest in physics, in engineering and chemistry, I figured out, okay, the way to make an impact is to be a clean tech entrepreneur, study chemical engineering, because that seemed to be the biggest way to have an impact in the clean tech space. And yeah, ultimately, I decided, like after going through college, that I really wanted to understand what does world-class engineering look like? What does world-class manufacturing look like? What does it look like to be a big player in the resource space? And I wanted to brush up the chemical engineering expertise. I remember talking to a mentor at the time, and I was telling him, oh, I'm going to go work at Shell at an oil refinery, and he's, oh, it's chemical engineering with a capital C, right? So I definitely went there to build up a lot of those like real world hands-on experience and beef up my chemical engineering creds.
Yeah, and what do you like? I guess I have a follow-up question here. What do you think was like your biggest like learning in terms of, was it more so that like you understood industry practices, or was there a certain philosophy in terms of how to like approach engineering that you picked up? What do you think was the biggest learning, if you don't mind me asking?
Yeah, there are a lot of things, and we're now talking about a couple of years ago, so my memory's a little blurred. I don't remember if I have a feeling some of these things were already nascent, but let's say the chemical engineering, the experience at Shell cemented this. My biggest learning, let's say, in the kind of the clean tech space, starting from first looking at it at the age of 14 till up until the present, is the most important thing that matters is really like density and concentration, right? So energy density matters a lot. We can lament fossil fuels. Ultimately, there's a reason we moved from wood. And historically, frankly, we had Dutch windmills, we had water wheels, we had Archimedes had the solar concentrator, things like that. So ultimately, we move towards fossil fuels because they're super energy dense. What that means is that they embody, through the chemical bonds of the fuel, they embody huge amounts of energy in a small space and in a small space as well as mass, right? And so in the kind of the resource space, that matters a lot. If you can deliver society a lot of energy in a compact and convenient aspect, that provides a lot of value. Can you do it efficiently? Can you do it cheaply? So a lot of these things fall for energy density. And obviously working at Shell at the oil refinery, you start to see that. You're literally doing engineering calculations. You're comparing it against other sort of competitors, let's say, to fossil fuels. And you're like, okay, no wonder fossil fuels are winning out in this case. The oil refinery, one of the units I worked on, the FCC unit, fluidized catalytic cracker, it would process 120,000 barrels of oil per day. Okay, and a barrel is 42 gallons, right? So it's just mind-blowing amounts. And if you do like the BTU value, huge amounts that are going through that. And then total refinery was 250,000 barrels a day capacity. So some of these aspects of energy density matter a lot. It's also why nuclear energy, a huge potential boon to society, because the energy density is way more bigger than any of the fossil fuels as well. So energy density is a main sort of thing I often go back to that really matters a lot, energy as well as resource density. The same thing applies for a lot of the metals, right? You have a copper or a lithium mine that basically same jurisdiction, same infrastructure, same sort of technology that you can employ, same workforce. If one of them, has a concentration of, let's just say 5 grams a ton, the other one down the road has a concentration of 20 grams per ton. It's going to make way more sense going after the 20 grams per ton because it's way more concentrated. You can have a smaller facility for the same amount of product. You can use far less energy to do the processing, things like that. So that's something that really matters a lot at pretty much every level of the energy resource nexus.
Yeah, I think the thing that separates like productive climate enthusiasts and non-productive climate enthusiasts who are just being like emotional and just are cause driven is like understanding the math you just described.
Yeah,
And
I couldn't agree more. I'm an environmentalist, and in some sense, when I first started, I didn't understand a lot of the realities, right? I was a big proponent, let's say, of biofuels in college. I spent all 4 years looking into biofuels. I was super into it. I mapped
right.
every single bio refinery and plant in the United States on a Google Maps a decade ago, things like that, right? But then once you start to look at the math and do the things, I think a lot of the people haven't done the math, or let's say they get lost in math and something else, right? You kind of I think life is a lot like this too. There are like a few key concepts for certain areas, and if you pinpoint the one or two really key points, then that's the biggest thing. And again, in energy and resources, that's one of the biggest aspects. It's the kind of the density, the concentration. Since I mentioned biofuels, I'll mention another one that kind of matters a lot. You see it a lot in kind of nature, basically, but kind of like a surface area to volume ratio is a big deal. So I remember learning at the time that it matters for solar panels as well, actually, right? So if you think about the light hits the solar panel, or let's say it hits the algae, right? So for an algae kind of thing, and it's a square thing, like it's a flat area you're hitting, right? And all the levels of algae below, or if you think about it, if you had a solar, instead of it being a panel, if it was like a cylinder, you wouldn't penetrate to the lower levels, right? So you're limited on like a second dimension. You're limited on like a 2 dimensions. Whereas like a chemical reactor, like an oil refinery with a whole vat of oil that becomes gasoline, it's 3-dimensional type of thing, right? So I probably haven't explained that very well, but basically surface area to volume ratio is often a big deal in a lot of systems.
Yeah, I think that was such an interesting way to frame things. I wish like this got taught to me in school. The
Yeah,
surface, yeah, it
sorry.
wasn't. So no, I mean, I've taken like my fair bunch of like chemistry and physics classes, but like this is such an interesting way to frame things because
Yeah.
first principles, like if you understand physics, like it's not a hard thing to grasp, but it's just how you framed it that I found very interesting.
Yeah. Honestly, it's funny because a lot of these sort of key lessons I've learned and like methodologies that I go back to sometimes to evaluate things, maybe I'm not giving enough credit, but I think most of them I was never really taught formally. It was something I figured out and picked up myself over time. It wasn't
And
usually in a course or a specific class or anything like that.
if you don't mind me asking, and because I've done, I honestly like with most of like my startups or finance or investing understanding, it is completely outside the classroom, almost completely. Like I would spend like at one point I had zero social life. I would spend 5-6 hours a day just like reading as much as I could. Did you have a version of that, like where you just were like reading a bunch of engineering blogs or reading papers like in college? What was your version of that, if you don't mind me asking?
Yeah, a lot of my life, right? I said even from a young age, I was reading all the literally, I kid you not, it wasn't a giant school, but literally it was in my middle school, literally every science book in the entire library. I remember also in college, sometimes I'd be staying up late, I'd get lost in what I call Wikipedia wormholes, right? And you start clicking things and it's
Yeah.
everything. And then you go to the next one, you read everything, the next one. And as I mentioned, like things like looking into all the different energy sources and the different resources and where they're produced. Yeah, actually, in fact, in college, a lot of it was energy focused. And as I learned more, I realized the resources were also a big deal, the metals and the materials. So the last couple of years has been reading a lot about different materials, different metals, where they're produced, the mines, the refineries, the smelters, different processing aspects. I had to learn all these different aspects of chemistry. Chemistry is a really broad science. So initially, let's say I had certain more aspects in kind of physical chemistry and or organic chemistry, and I've had to learn a lot about inorganic metallic chemistry, different things like that.
Yeah, I was gonna say if you had to think about this from like a curriculum standpoint, like you started off being obsessed with organic chemistry, which is all your biofuel stuff, and now like you're doing it for all practical purposes. And I apologize if I'm oversimplifying. Like metallurgy, which I was taught is inorganic chemistry.
It is, yeah.
So it's interesting. You so you do this thing at Shell, but then you take like a sort of lateral shift to Nexent, which is a consulting firm, from what I understand. You do a bunch of really seminal work on metal extraction and processing. Or as we just discussed, you went from organic chemistry to inorganic chemistry. Let's talk a little bit about that transition and your experience working at Nexent.
Yeah, it was difficult. I had started to go into that anyway. But then I remember having a conversation with one of the bosses there, and it was like certain aspects, things I didn't necessarily anticipate between the energy side versus the mineral side. I'll give you one example, right? I think this is the specific example. So cobalt is used a lot in the batteries, right? So I wrote a report on cobalt processing technologies, economics, that kind of thing. One of the things I didn't anticipate, because I don't have really a geology background. I've learned some aspects now over the years. At the time, my knowledge is pretty limited. A lot of the metals are produced as a co-product, right? Oil, typically, let's say oil is usually oil, gas, and water, right? So there's three things. There's not really much complication. Oil is a giant mixture, but it has different properties. But let's say it's a hydrocarbon. It's carbon and hydrogen, right? Mineral ores is, there's oxygen, there's sulfur, there's nitrogen, there's a million metals. A mine might produce some metal and then might get value from all 9 different metals that they sell eventually, right? So cobalt is actually usually a co-product. There are some aspects where cobalt is the primary product that you produce. In many cases, it's a byproduct of nickel and copper mining. And it changes some aspects of the economics and the technologies you utilize. And in many cases, like you're not actually like optimizing the technology and the processing to produce cobalt. You're optimizing it to produce copper and nickel and things like that. So that's one example. So it was interesting. I wrote that report. I learned about lots of different technologies. I learned about the markets. Most of the cobalt basically comes from the Congo. And a lot of these leading papers, Washington Post, et cetera, and New York Times, I think in the United States have written about this, but there's aspects of basically like child labor and slavery, genocide, things like that, bad mining practices in the Congo. And effectively, almost all of that output from the Congo, Democratic Republic of Congo, it goes off to China. And so China does all the processing. So Russia is basically the kind of commodity superpower. They produce all the raw resources of the world, a lot of them, one of the leading producers. And then China does all the processing, the refining, and then eventually the manufacturing into the final product, like the lithium ion battery.
I didn't know that Russia was like, okay, I need to do some reading.
Yeah.
I don't think this is well covered.
No, it's really not.
Yeah.
The resource space in general is not really well covered. Yeah, people don't tend to do the math as we talked about earlier, but then they also tend to overlook a lot of these resources in the supply chains. People are talking now more about the supply chain, and definitely this war in Ukraine, between Russia and Ukraine, is quite timely because, like I mentioned, Russia is often a leading producer of a lot of these exotic metals, and so there have been aspects of that. And I think recently China has announced, they've done this multiple times over the years, but I think the most recent one is they've restricted exports of germanium and gallium, which are exotic metals that go into electronics and other things.
And you've begun this sort of academic exploration. You're learning these new things, and you've obviously written a bunch of stuff. You're in this almost sort of professional academic mode, if that's.
But the job that Nexen, it was a professional job, right? We'd write the reports, we'd have clients, and the customers would buy the reports.
So it was still like fairly. It was like a client-driven research
thing. It was completely commercial, right? So I had to provide value, that the customers saw value into it. And my pitch actually at the time was, and it's still basically the same thing now, is if you're really trying to move away from a fossil fuel-driven economy and go towards renewables and alternatives, you're really moving from a fossil fuel economy to an exotic metal economy, right? So instead of the bottleneck being purely like oil, coal, natural gas, it becomes the copper, it becomes the lithium, the silver, the gold, the platinum, some of the rare earth elements, things like that. And in effect, a lot of established players have focused on that past paradigm. And I think we need to start thinking about some of these newer paradigms with the metals.
You publish a bunch of these reports, and you're obviously interacting a lot with industry partners, clients, and so forth.
A couple of years ago, yeah. I don't do that anymore.
Yeah. And I guess my point here was like, how did that inform, your decision to start Determinant Materials? Because starting a company like to make SaaS is like a big headache. Like you actually have to like incorporate, like you have to make a commitment. There's a time commitment. There's like financial commitment. But you decided to do a company in the space, which is incredibly hard. How did you make that decision? What informed that decision? Just talk a little bit about that process.
Yeah, so the drive was there from, like I said, the beginning. It was basically, 16 years old, 11th grade or 12th grade, college application process. I figured out that's what I wanted to do. I went to college. I was in the Boston clean tech community. Basically, we have all these hubs now, but back then it was really just Boston and SF. And in some sense, clean tech really that was the major more than SF even. And so I explored a lot. I got to see different things. I thought about EVs, I thought about fuel cells, I thought about all this stuff, solar, wind, batteries, etc. And so I was looking for something for a while that I felt would really make a big impact. One thing is basically I was auditing an MBA supply chain class at a nearby school, Babson College. This was this was a decade ago. So this was actually, it was right before I graduated. And one day the professor, we would look at different case studies of different industries, right? So one day the professor, we talked about the electronics industry. He whips out his phone. He said, did you know inside this phone, there's 100 to 1,000 times the concentration of gold and other metals, right? So I knew that there was copper. I knew that there was tin because I had taken a circuits class, 2 circuits classes, and I had actually made some of this circuitry. Nothing as complex as a modern day smartphone, but I knew that, but I didn't know that there was gold. I didn't know there was silver, platinum, et cetera in there. And that was really interesting to me. Again, the concentration thing, right? So because it's so much more concentrated, that means you have to go through far less material to get the same amount of useful metal out. And so that was in the back of my mind the whole time. As I learned about it, I realized, hey, look, electronics is the fastest growing waste stream in the world. It's such a concentrated source of all these needed materials. Right now, the vast majority of it just gets landfilled, incinerated. Of what gets recycled, it's almost all going off to developing countries, getting burned, open air burned, acid bath. It was back of the mind. And as we mentioned, it was not really the whole metal chemistry and the metal processing was not something I have a background. Frankly, it's a background that almost no American has. There are barely any mining colleges in this country now. Very few mining, very few mineral processing, extractive metallurgy. So I was starting to kind of digest some of those things. Like I said, I was at Shell that kind of built up the chemical engineering, the manufacturing expertise. Nexent was good because I wanted to explore these other domains. I wanted to learn about these other metal industries. So I got to dabble in the different things. And ultimately I just decided, I was like, okay, look, I have this interest. This is an idea that keeps sticking with me. It's something I want to pursue. So ultimately, I decided to leave. And I was tinkering on the technology for a while, right? And then I was traveling the world. I went to India multiple times because that's where a lot of electronics are. I processed. So I worked with an electronics recycler, a gold refiner. And I basically did hands-on with them, burned the electronics with them. I inhaled the fumes, did the aqua regia acid processing, saw the cyanide processing, et cetera. So I really understood the problem really well. And so I felt, okay, I understand the problem. And then eventually I came up on the beginnings of the kind of the technology that would meet the solution that I had identified.
And your core product is that you came up with after all of this thought is the metal extraction product, right? And the core technology is called micro refinery. Like, what was the process of conceiving that idea? How many iterations did you have to go through in terms of product development cycles to get to the current state of where the product is?
Yeah, so I think often it doesn't quite happen as much as in kind of like the deep tech space. But I think often people are like, hey, I want to start this company and I maybe I have a sense of the problem and I'm going to start the company. So I'm going to go assemble the team and raise lots of money or go into an accelerator, apply to an accelerator and off to the races, right? But again, my learnings in the clean tech boom and bust, massive amounts of money were spent in the 2000s and kind of the 2010s, and even are starting to right now again in kind of the climate tech with the rebranding of climate tech. But frankly, a lot of the companies out there, and it's not even just startups, it's existing companies too, it's governments, it's every level. A lot of them aren't really actually, in my opinion, making the world a better place. They're not actually solving the problem because they don't really understand the problem. So to me, it was that Abe Lincoln quote, if I have to cut the tree down, I sharpen the axe for 55 minutes, and then I chop the tree down for the 5 minutes. So I wanted to put effort into really understand the problem at a really deep level. Why is it that electronics are so hard to recycle? Why is it that we are just mostly open air burning it and not capturing a lot of the value? Why is it that we're just arbitraging the cheap labor and lack of environmental health standards in developing countries? Why is it that we're often landfilling it? So I wanted to understand at a deep level, what is the current global web, the supply chain of this? How does how does the Mac that I'm talking to you through at end of life, how does it eventually travel through the supply chain and end up where it ends up? So it was talking to people at the EPA, it was interacting with them, talking to people in the electronics recycling chain in the United States, going to India, doing the processing with people, finding the dealers that deal with certain electronics, learning where the metals are concentrated, reading all the different research papers and learning about extractive metallurgy, reading old books from 100 years ago about metal processing, things like that, and lots of trial and error. And as I identified basically the kind of the problem and the challenges with the existing incumbent technologies and incumbent like supply chains, that's when I came to realize what the solution could look like. And from there, ultimately, what the technology could look like. And our plan is basically electronics are a distributed resource, right? There's so much of this stuff. It's the fastest growing waste stream in the world, but it's not like a gold mine, right? With gold or like an oil reservoir, you've got it all concentrated in one space. Here it's distributed throughout the world, right? In communities and cities, big and small, and towns. Our thesis basically is we have these distributed cookie cutter modular units, the micro refineries, based all over communities all over this country and then eventually the world. So that's what we're doing. And yeah, the technology is basically, I have to be a bit careful with my lawyers will get upset if I talk too much of the details, but basically we're pioneering a cleaner process that doesn't do any of the acid leaching, that doesn't have any cyanide, doesn't have any burning. It's a much more efficient process based on our really deep understanding of kind of the feedstock, the characterization of what we're processing.
I just want to make sure I understand here. When you were designing this process, which is really your core technology, the microrefinery technology, what were the sort of variables that you were trying to maximize or minimize?
Yeah, so that's a great question. So one of the big things, so if you've ever read Peter Thiel's book, 0 to 1, right?
Yep.
He talks a lot about what are some of the key characteristics of really dominant businesses and dominant technologies, et cetera. And he covers the clean tech segment. And it was a lot of his lessons are what I observed, that what ended up happening a lot in kind of the clean tech bust that I had referenced earlier is people were making like really commodified products. So they were just like producing they were saying, okay, we're going to produce energy. So we're producing electricity or we're producing some kind of fuel. There was not really much differentiation. The capital costs were enormous, ginormous. And this is a problem throughout basically all of hard tech, deep tech, right? It's often why a lot of people want to rush towards software because in some sense, the capital cost is lower and the capital efficiency of a lot of these units weren't great. So what I was trying to do is I was trying to figure out how do I build a small facility that's cheap and effective, that I don't have to have multiple rounds of VC fundraising, for example, or giant like loans, et cetera, in order to get to meaningful revenue. So I was trying to maximize capital efficiency in effect. Even in investing, a lot of businesses over the long run, they're doing well because they have public market investing. They do well if they have capital efficiency, right? So meaning, can you produce high revenues and free cash flow profits from a small initial investment in effect, right? So I was trying to maximize that. And part of that is, okay, am I running processes that have to have huge capital equipment? How long is the processing time? That's a huge aspect of it, right? So it's a very chemical engineering thing. They call it space time, right? So if the reaction, or in my case, if the process is taking 5 days versus 1 hour, that means I can turn the unit over and over. So it means for a small volume, a small facility, I can have huge throughputs through it. And thus I can have huge revenues for it, right? That's a big aspect. Again, what I'm processing is a big aspect. If there's a lot of material value in certain electronic streams compared to mineral ores, then that means I can have high amounts of economic value out of that. The amount of energy I'm using, do I have an energy intensive process, waste generated versus having a zero waste type of facility? These are all different aspects of that. It makes regulatory better or worse. It makes the operating costs better or worse. Complexity is a huge thing, right? Running an oil refinery, it's inherently a really dangerous system, right? You have extremely flammable, explosive materials there, and you've got a giant complex system. I think that's a big aspect. Scale definitely helps, but people often talk, what they teach you in school and what the dogma is, basically you build a giant facility, right? You just as big as you can get, right? But the complexity tends to multiply, right? It becomes exponential. So just to run the oil refinery, for example, to run it safely, you need massive amounts of skill sets across a gamut to make it safe, and then to make it reliable, and then to make it economical, right? So when you have a smaller, more efficient facility, the burden of labor that's involved and the complexity involved is much lower. You can get it done and you can be economical at a smaller scale, and then you can cookie cutter it, right? So that aspect of, can I modularly copy this everywhere? That was something I designed for as well.
So is it fair to, just to conclude, is it fair to say that you optimize for modularity and like you try to maximize modularity and minimize complexity?
Yeah, complexity in the operation, minimize that, maximize modularity, minimize capital costs, minimize energy usage, minimize the kind of processing time that it takes, minimize waste, things like that. So there's a lot of variables that went into it. And that's how initially in the beginning, like I had the solution in my mind, like, okay, this is what it would be like. This is what the microrefinery would be like. And then it took time to come up with the technology that I actually meet that. Again, it's what I talked about. It's like that design. Okay, I went out in the world, I learned what the problem was, I came up with the design. Then I came up with the engineering, the technology, right? That met that. And then finally, now I'm building the business and I'm growing the business such that I can get these out in the world and serve the people in society.
Okay. And how many iterations from start to present did you have to go through to get to a point where you were like, this is something I'm happy showing to like a potential industry partner or like a client?
It's honestly, it's not really something I counted, right? In the beginning, I was literally like benchtop Bunsen burner type of thing, like dissolving things, etc. Reading about a lot of things. I think like the improvement, especially as a technology company, is something that you constantly want to be iterating and trying new things. So it's been more of like a continuous process as opposed to here are the discrete prototypes, let's say.
So it was basically like continuous improvement. There was no like discrete, like sort of product development phases that you'd outlined.
Yeah, it was more continuous, and obviously it came down to the resources I had also. With the amount of capital that I can invest, the time and energy, other aspects of trying to get the business off the ground were involved as well. And there became a phase shift when I discovered some of the key aspects and kind of the key secrets of the business. That's when there would be like a big shift into what the design and of the prototype and the process were.
And it sounds like you funded all of this yourself. Can you just talk about how you, because this sounds a little expensive. Have you just funded the entire product development yourself? Are there grants, funding? Can you just talk about how you funded this entire?
Yeah, I got some kind of small grants, but for the most part, I was really self-funding it for a while. I think when you're bootstrapped, you as an entrepreneur, again, to compare with what I mentioned earlier, some people are launching companies and just raising immediately. They don't really learn the hustle, I think, as well. I think they eventually do, but maybe in the beginning they don't learn the hustle as well. I had to be really like on point and figure out, how do I always minimize costs? How do I get people to do things for free, honestly? How do I kind of leverage the resources that I have access to right now when I was capital constrained? But yeah, so ultimately we built the kind of benchtop prototype system, did the processing end to end, recycled electronics, produced gold, made a sale of the gold into a jeweler. And then from there, I closed a fundraise. So I have raised venture capital now.
Okay. And is that something you can talk about, or is that something you'll be talking more about later?
Yeah, I'm curious if you have any questions.
Okay. Yeah. Like what is that? How much money do you guys raise, if that's okay to ask?
Yeah, I think kind of those specific details of the raise, we're keeping to
Okay, that's fair. That's fair. And did those conversations were they already material? Like before, like you were able to make a big sale in terms of like your extracted product, or did they become material after like you sold your extracted product? If that makes sense. Did you have like material interest like before? Because I'm just trying to understand like.
I wasn't even, it's interesting. You talk to startups and each of them, I'm sure, has their own story, but I was even somewhat removed I was planning to bootstrap the business for a while. And for a couple of reasons, I decided, hey, now's the time to raise venture. And so I was pretty into the startup realm, the Boston startup realm, like a decade ago. But to some extent, I went off to, back to engineering mode, learning the chemistry and the physics mode, that kind of thing. So I was actually quite removed from the startup realm until a year and a half or so ago. So yeah, no, I had to basically develop the network, which you come to realize with the fundraising, it's a lot about, in business in general, I've come to realize a lot about this. It's a lot about relationships, right? So it was cultivating the relationships, speaking to other entrepreneurs. Honestly, I owe a lot of people. They've helped a lot with the fundraise. You get introductions to investors, identifying who might be most open to helping and who could be the best partner with you moving forward. So definitely there's a lot of aspects of that are quite different from the engineering and the technology side. So I had to navigate that and learn that. And honestly, Twitter, where we connected, has been a monstrous help. I know one of my startup friends, two of my startup friends had told me I need to get on Twitter. I didn't have a Twitter until I think beginning of 2022, actually. Yeah. So last year is when I got on Twitter. So I didn't have one that I got on it. And it definitely has been a big help to connect with other entrepreneurs as well as investors.
Yeah, I think I've just come back from like a networking event actually before this podcast.
Okay, cool.
And as soon as I finished, as soon as I got out of the room, I'm not joking, I started going back at Twitter. Yes.
I'm sorry, you started what?
No, I said I started going on Twitter and I started seeing like the drama, like what's what, like who's doing what in the startup space, and also the more fun, like idiotic in people. Like Twitter is so much fun.
Yeah, not to make this a free advertising Twitter, but
Yeah.
one of those friends described it as like what LinkedIn was supposed to be. So when I was in college, I even took like a co-curricular or something where it was like, yeah, networking, like how do you network? And so I would go to the events at Harvard, MIT, in the Boston area. I'd collect business cards. I'd shoot them all emails literally right after it, even if it's 10 o'clock at night. And it really, I add them on LinkedIn, and it frankly didn't do anything, because in the end, people engage, and this is not even professionally, this is also personally too, right? People want the constant, it's marketing too, right? They have things like the rule of 7, right? You have to see things 7 times to get in your mind, right? So people, they also say out of sight, out of mind, right? So people need to see that. They need to have the engagement. You need to become a known entity to them. They have to feel comfortable with you, that kind of thing, right? That doesn't happen when you have a one-off networking event and then you don't see the person for 6 months, right? So Twitter is good because you can interact. You can hear people's thoughts, you can comment on their thoughts, etc. As a group, you can comment on things. So that's one aspect of that. And obviously that helps in entrepreneurship and it helps with fundraising.
Yeah, absolutely. In fact, like I think 2 things that have helped me professionally, I'm not joking, has been like Twitter.
Yeah.
And it's been my podcast.
Yeah.
My networking events have done almost nothing for me. Absolutely nothing. Like my first like real internship was because of this podcast.
Okay.
Yeah. So
I agree.
Yeah, I honestly just went there for the free food. I'm not even lying. Yeah. Yeah, we've spoken a lot about like how you came up with the technology. What has it been like to interact with these industry partners about like actually adopting your technology?
Yeah, we're an early stage company. This was literally the first fundraise, the first kind of injected capital, outside capital. We're really beginning that journey. But yeah, we've engaged. Our plan eventually is to get into other markets like electronics, defense, automotive, space, etc. But in the beginning, we're actually focusing, not exclusively, but some of our kind of like initial target customers is the jewelry industry. What we've identified is a lot of the value in the electronics is actually the gold. There's so much talk about lithium and cobalt and nickel and rare earth elements. And just based off of pricing and based off of how much there is there's not that much economic value in that at the moment. A lot of the value is in the gold. So we're targeting gold. It's actually in some sense also like one of the hardest things to produce because there's such minute amounts of it. So we're producing gold. And again, that Peter Thiel 0 to 1 kind of mindset, we're not looking to just produce a commodity product that like no one has any real desire to buy. We're trying to produce metals and materials that people are really eager for, right? We're looking for like the hair on fire type of customer that really wants to buy a product. And so the value proposition is we can say, hey, look, we know exactly where this metal came from. We know how it was produced here. It was sourced from here. It went to our facilities. It was produced cleanly, effectively. It went directly to you and your manufacturing partners, right? So there's that clean, traceable supply chain. Again, we're zero waste. We're not doing the nasty, dirty, dangerous leaching, whether it's acid leaching or cyanide leaching or something like that. We're not doing any burning. So there's value there in the fact that we have an ethical, clean, traceable source. It's low carbon, etc. And so a lot of these different industries, from the end markets, from the government to automotive to electronics, they are keen on this thing. But I took the NSF I-Cores program. It's a lot about like the lean startup type of method, doing customer discovery and that kind of thing. And that's how I initially came onto the target of the initial customer as being like these ethical jewelers. So the jewelry industry, not just because of this, but consumers have become more aware of kind of like the ethical aspects of jewelry because the movie Blood Diamond, Leonardo DiCaprio, like a decade or more. So people have been thinking about the diamonds, the gemstones, where do they come from? Are they coming from conflict areas? Or are there warlords and terrorists that they're financing? So the same thing is happening in the metal space, right? So there's all these ethical jewelers in lots of big cities that in the United States and around the world that want to know where the metals come from, and they're keen to basically have that clean source from us, that they know it's not conflict, that can tell them exactly where it came from, they can see the factory, and they know it wasn't a dirty, nasty process that ripped up the earth and burned things and leached into the rivers, etc.
And what do you think are your core challenges in terms of scaling your core technology, which is a micro refinery technology? Just technically speaking, what are the challenges in terms of scaling it? Like in terms of increasing, as you previously mentioned this, which is if you make things bigger, it just increases complexity, like operational complexity. So could you just touch base on that a little bit and just educate us?
Yeah, and like that surface area to volume ratio thing is big. So if you, for example, if you have some chemical that you've made in the lab, right? You figure out how to make some new design or pharmaceutical or something in like a little Bunsen burner beaker, right? That sort of surface area to volume, like the surface area of the Bunsen burner versus the volume material you have, the heat that's going towards it, the certain other aspects, that changes when you have a bigger scale, right? You're actually typically, when you're getting bigger, right, you're having less surface area to volume. So that's really one quick example, right? So the heat transfer changes. I think I remember when I was at Shell, heat exchangers are a big thing. I remember we would do like equations off of if there's an emergency and like the relief valve, the depressurizing valve has to open, the material can only move out the speed of sound. That's the limit, Mach 1. So there's aspects you have to think about the physics and chemistry, right? So as you're scaling the size of it, the actual underlying physics and chemistry, the laws are the same, right? But the specific condition that you've created for it becomes different, right? So the engineering equations in some sense become slightly different. So definitely certain aspects of the complexity change. The other thing is like with our operation is I was building it with certain pieces of equipment, right? That would do it at a small scale. You have to figure out, okay, I still want the same unit operations. I still want the same end-to-end process, but now I have a bigger scale. Are there cheap available equipment that I can utilize that does every part of the process? So that's one example. Then you're building a commercial enterprise, right? Like you have to think about hiring, right? So can I find the skilled labor that is economical and you can run the facility? And again, with the safety and complexity, do you have all the different skill sets you need to make sure that this runs safely and efficiently and economically, right? So those are some of the things you have to think about.
And what do you think are the challenges in terms of scaling, like the actual like commercial adoption of your solution?
So one of the learnings at Shell actually is I ran these units called fluidized catalytic cracker and the gasoline hydrotreater. So what that would do is it would take a lot of the like low value, heavy oil that's in the barrel of oil, and it would turn it into high value, high octane gasoline that you could fill up at the pump for your sports car. And one of the things is I was in charge of the unit, and you'd have outside companies that would try to sell us the technology, right? They'd want us to switch our technology to them and contract with them. So what you actually find a lot in the kind of startup space, and I think a lot of the investors also push for this, is new technology companies, they often want them to license the technology, right? And what I found is like those companies are a dime a dozen, right? I had people trying to wine and dine me as like a lowly entry engineer in order to use their technology to switch over. So there's a lot of competition and there's not really much differentiated value at a lot of time. If you look at you go back in history, you look at like Carnegie Steel or like a Standard Oil, what a lot of those industrial companies of the industrial era showed is basically you have a lot of the value by owning the technology and owning the full value chain. You own the technology, you own the manufacturing facility, you produce the branded product, and you have that direct line to the customers. So that's what we're building at Determinant Materials. We're trying to completely revolutionize the way materials are produced And we're trying to brand and have a new type of material that we're selling to certain end markets.
And is there like I mean, you don't have to name names here, obviously, but is there an interesting like customer interaction you've had that really like sticks to your mind in terms of
Yeah, a lot of them have been really interesting and engaging. We recently, I think I can announce this. So we recently got into a program called Third Derivative, and they're really focused on climate tech. And they have a lot of key partners, big name companies and big name investment firms through it. So we're actually, a lot of the value add for that program and why I was so interested is it's about engaging with all these different companies in different verticals and different sectors that we're interested in. But for what we've done so far, we've been pretty heavily focused on the jewelry sector. And it was interesting going into this. I had no idea the jewelry sector was so complicated. There's all these different aspects of producing jewelry. In some sense, I've had to learn in order to have that customer discovery, in order to provide the value to the end customer. One of the things that with the real world that is interesting and different than a lot of aspects of software is with supply chain, you got to figure out how to drop your material into the supply chain, right? So if I produce gold, for example, okay, there are potential purity requirements, but then there's actually physical requirements too, right? It's, am I producing in a form that the customer, the jeweler, can use and drop into her supply chain that she can have her manufacturer make her gold necklace or ring out of, right? So I had to learn about jewelry casting and different aspects of that. Who are the actors along the supply chain and things like that. So it's quite interesting and engaging. And eventually that starts to build like the moat in sense for the business, right? Like you contract with the customer, you've dropped your material into the supply chain, they start to work with you, etc.
Yeah, that makes a ton of sense. Yeah, I think helps elucidate on what it's like to truly interact with an industry partner. For example, like I worked on a startup project, which is to essentially help connect financial advisors and customers better. Turns out like an important aspect of this whole thing is something called FINRA check, which
Yeah.
is and that's like really important part. I'm sorry?
The financial system is pretty regulated, right?
Oh, incredibly. Yeah, and I think if we ended up like pursuing and like scaling, like we probably would have had to have a subsidiary that was like a registered investment advisor
Yeah,
or
yeah.
something like that. It's super weird. So I think I get your experience. I guess I wanted to close on this. You're obviously, I think you're an industrialist in every sense of the word, right? You're like
Yeah.
a baby industrialist trying to be like a big industrialist. You also, I'm sure you keep abreast with other technologies that are happening that are not in your domain. Is there something that's not in your domain that you're excited about?
Yeah, it still is in my domain, but let's say I'm not at the moment pursuing a startup in that. We mentioned earlier about the density aspect and that being my conclusion. Looking at all these different technologies over a decade in the resource space, examining everything, my conclusion was a lot of them weren't really actually making an impact and having a really positive net benefit. Electronics was one thing, this electronics recycling, and was one thing that I landed on as something that could make a big difference. The other thing was basically nuclear energy, the whole kind of like nuclear aspect of things. Again, it's super energy dense. It's really a shame, let's say, that we made so much progress up to the 50s or so, maybe even a little bit of the 60s in the nuclear era, and then that stalled for a long time. But that has started to reinvigorate again. So that is quite interesting. I think if we really maximize, we can produce a lot of these materials by having advanced recycling technologies like what we're producing. So that'll produce all the key metals that we need. And then to produce the energy, if we can really build out nuclear dramatically, for a while, again, it's regulatory, heavily regulated. I think the stat is like the nuclear agency hasn't produced new reactor designs in like decades now. But what's happening now is you're having these small modular reactors that are supposedly inherently safer. And it's a similar thing, right? Distributed model, high density processing, cheap, safe, effective, modular, cookie cutter. So those are quite interesting. And if I wasn't working on the electronics recycling, I'd be working on something like that, the kind of distributed energy production in the nuclear space.
Yeah, it's interesting you mentioned nuclear. Like today, we've actually spoken like a lot about nuclear, surprisingly. Like on a podcast that was supposed to be about like a metal extraction company. Yeah, okay, what happened today? Oklo it went public. Like it was like a nuclear.
Okay, I didn't know.
Oh, like the nuclear startup did. Yeah, yeah. First of all, Sam Altman apparently had a SPAC. Huge
Okay.
shock. I feel like that guy's got his fingers in everything. And his SPAC is like taking Oclo out public. And I'll be very honest, like I never thought in my life like I'd see like a nuclear company go public, let alone two, because New Steel is, I think, is already like a publicly traded like nuclear company. So
It's heavily owned by Fluor, the big engineering company. I know because
which company is that?
Fluor is a big engineering company. They do design and engineering construction. They'll build things like oil refineries, chemical plants, even probably highways, bridges. So
Oh,
they
cool.
they own a lot of new scale stock.
Nice. Oh, this is one more like case study to do for the podcast. Nice.
Yeah. So talking
yeah.
about nuclear. Yeah. Again, the reason I brought it up is on kind of the energy side. It was something I identified in high school. Is something that's going to be a big thing. I remember I got some scholarship from Northrop Grumman, the big defense contractor, and the journalist interviewed me, and I talked about nuclear energy and stuff like that. I see this as well. It's similar. You have a better way. If you dig into the way metals are produced in mining and material processing, it's scattered all over the world. It's wildly inefficient. It's subject to all these geopolitical tensions. If there's a strike somewhere, or if there's an embargo, or that kind of thing. So I think having like local secure supplies of metals and of processing, of taking the kind of the waste that we produce in our communities and getting value out of it, the concentrate aspect of it, I think that's something, it's somewhat similar with nuclear, because you can have high density, you can have advanced technology. And with the modular reactors, you don't have to have the giant facility that is, again, inherently more complex, inherently more needs 1,000 different specialties to make sure it runs safely and stuff. So yeah, the SMR technology is quite interesting.
Yeah, absolutely. I think if I was a better engineer, and I'm not, I think like I need to like work a little bit in terms of my engineering understanding. But if I was like a pure like engineering person, like nuclear is the thing I would work on. Like absolutely.
Yeah.
Yeah. But thank you so much for coming on the podcast, Nikhil. This was lovely. I actually learned a lot. I did not know jewelry was that there were that many components to the supply side of jewelry. So that was interesting. Yeah, thank you so much for sharing your time. I really appreciate it.
Yeah, thank you for having me on the podcast.
Yeah, thank you. All right, take care.
Bye-bye.